Okay, one more example. Let's find the parametric equations of the line tangent to f of x equals sine 3x times sine y at pi over 4 comma pi over 4 in the direction of the vector 1 comma negative 1. All right, so we're given our point x naught y naught. That's going to be our pi over 4 comma pi over 4. And then our direction vector is 1, negative 1, which is still not a unit vector. So let's make that our first step to change our direction vector into a unit vector. So we're going to take 1 comma negative 1 and divide it by its own magnitude. And this one is not a nice one. We got 1 squared is 1, 1 squared, negative 1 squared is also 1. So we get square root of 2 on the bottom. We're going to have 1 over the square root of 2 comma negative 1 divided by the square root of 2. So there's our unit vector. So we have our point and our unit vector. And again, what we need for our equation of the line, we need a point on the line. Okay, which is, let's see, they gave us the x coordinate and the y coordinate. And we're going to find the z coordinate just by plugging into the function, just like on the last one. So I'm going to plug in f of pi over 4 comma pi over 4. So we have sine 3x times sine y. Let's see, y is pi over 4 as well. Okay, unit circle, 3 pi over 4 is over in the second quadrant where sine is positive, and sine pi over 4 is where sine is positive as well. So these are both square root of 2 over 2, square root of 2 over 2. So that is 2 on top and 4 on bottom, or a 1/2. All right, so our z coordinate of our point on the line is a 1/2. All right, next up, direction vector. Let's see, we're going to get the x component and the y component from the unit vector, and that we found over on the left in blue is 1 over the square root of 2, comma negative 1 over the square root of 2. And then we're going to have to fill in that last component with a directional derivative. All right, to get our directional derivative, we need the gradient. So let's calculate the gradient. All right, so gradient is made up of the partial with respect to x. So partial with respect to x, we're going to take the derivative of sine 3x, which is cosine 3x, times the derivative of the inside function, chain rule, we need a 3. And then times sine y, that's just a constant, that's just going to go along for the ride with respect to x. And then we do the same thing with respect to y for the gradient. So now sine 3x is the constant. It's just going to hang out as a coefficient. Derivative of sine y is cosine y. Okay, and I guess I could make that first component a little prettier if I pull the 3 out front. So 3 cosine 3x sine y, comma sine 3x cosine y. All right, now we know the directional derivative is where I dot the gradient with our unit vector, but first we want to evaluate our gradient at the point we're interested in, pi over 4 comma pi over 4. So we're going to evaluate the gradient at the point we're interested in. Okay, so we're going to have 3 times cosine of 3 times pi over 4 times sine of y, which is also pi over 4. And then sine of 3 times the x pi over 4 times the cosine of the y pi over 4. Lots of unit circle, but we just did most of this for the z coordinate of the point. So we've got 3 cosine 3 pi over 4. So remember, 3 pi over 4 is over in the second quadrant where sine is positive, but cosine is negative. So we're going to have 3 times negative root 2 over 2 for 3 pi over 4 cosine. Sine pi over 4 is a positive root 2 over 2. Need a multiplication there, not a comma. There's the comma. Sine 3 pi over 4 is root 2 over 2. And cosine of pi over 4, that's back in quadrant 1, it's root 2 over 2. We have already done root 2 over 2 times root 2 over 2, and we got 1/2. So this is going to be 3 times a negative 1/2. If I multiply those together. And then on the y component, we've got another 1/2. So this is negative 3/2, comma 1/2. Okay, so that's my gradient vector. Why are we doing this again? We need the directional derivative to fill in this last component. We're almost done. If we can fill in that component of the direction vector, the z component, with this directional derivative, I need to take the dot product of this vector, -3/2, 1/2, with our unit vector. All right, so we need to take our gradient vector dotted with our unit vector. So our gradient vector was -3/2, 1/2. And our unit vector is over there, 1/√2, -1/√2. And we will multiply component-wise and add. So we're going to have -3/2 times 1/√2 plus multiply y components. So 1/2 times -1/√2. And we've got -3/2√2 plus -1/2√2. All right, mercifully, we already have a common denominator here. So we're going to have 2√2 in the denominator. We're going to add those negative numerators, and I get -4/2√2. And I can reduce the 4 and the 2 and make that -2/√2. Okay, so technically, if you reduce that, you would get the square root of 2, but I think we've had enough arithmetic of fractions today. So I'm just going to leave that as -2/√2, and I'm going to take that up to my direction vector as the z component, -2 divided by the square root of 2. All right, so now I have the point on the line and the direction vector. Let's write the parametric equation. All right, parametric equations go x equals y equals z equals. The point is the constant parts of the parametric equation. So I'm going to take the x coordinate, the y coordinate of the point, and the z coordinate of the point. And then the direction vector becomes the coefficients on the t's. So we're going to have plus the x component, 1/√2 of our direction vector times t. Let's see, then we're going to have plus a negative, so minus 1/√2 times t. And then our z component of the direction vector was -2/√2 t. And those are our parametric equations. Let's go over to Desmos and hope that we got this right. All right, here's our function, sine 3x times sine y, wavy looking thing. And we were given x and y to be both pi/4. We calculated the z coordinate to be 1/2, so that point is on the surface. So far, so good. We can see that point A there. And we were given a unit vector, which was 1, -1. So we can see if we kind of look down on the xy plane, we're trying to find the tangent line that's going to be in that direction. And fingers crossed, there's the parametric equations that we found when we did our calculations. And all right, let's turn this around, see if it looks tangent. That does look like a tangent line. It almost doesn't look like it's in the right direction, but if you look down onto the xy plane, it lies right in the same direction as that unit vector that we were given. All right, so there we go, found tangent lines. In class, we're going to talk about finding equations of tangent planes.